expands our understanding of the universe. However, the methods currently employed come with significant limitations. One of the primary techniques used is called transmission spectroscopy, which relies on observing the starlight that passes through a planet's atmosphere during a transit. Unfortunately, this technique is most effective for larger planets that block substantial amounts of light and for systems with bright nearby stars. As a result, many smaller, potentially habitable worlds remain elusive, hidden behind the glare of their parent stars. Another challenge is the atmospheric composition itself. Exoplanets can have atmospheres that are thin or consist of gases that are difficult to detect. Additionally, many atmospheres can be obscured by clouds or hazes, complicating the interpretation of data. In many cases, the signals we receive from these distant atmospheres are incredibly faint, often buried beneath the noise of the star's light. This means that even when scientists manage to collect useful data, distinguishing the specific components of a planet's atmosphere requires sophisticated models and sometimes even a bit of guesswork. Moreover, our current telescopes and instruments have limitations in their resolution and sensitivity. While advancements are being made, such as the launch of space telescopes designed with specialized capabilities, the technology is still catching up to our ambitions. Telescopes located on Earth, for instance, are hindered by atmospheric distortions, which can blur the signals we receive from space. Observing from the ground means dealing with weather conditions and pollution, both of which can affect the accuracy of our findings. Lastly, the sheer distances involved create a time lag in our discovery process. The light we see from distant planets can take years to reach us, meaning that while we might identify an exoplanet today, we are observing it as it was long ago. As our techniques and technologies evolve, the challenge remains not just to detect an atmosphere, but to understand the complex interplay of its components. Despite these hurdles, the search for exoplanet atmospheres continues to be a promising and profoundly inspiring venture into the cosmos, one that may very well lead to extraordinary discoveries about our place in the galaxy. Astronomers have developed a structured system to categorize and name new exoplanets, those fascinating worlds outside our solar system. This process begins with identifying the exoplanet's characteristics, including its size, mass, and the nature of its orbit around its host star. Such details help scientists position the planet within a broader classification scheme, which includes categories like gas giants, rocky planets, and even icy worlds, similar to the planets we are familiar with in our own solar system. Naming exoplanets follows an interesting set of guidelines established by the International Astronomical Union, or IAU. When a new exoplanet is discovered, it is initially assigned a designation based on its parent star's name, often followed by a letter. For example, if a star is named HD 209458, its first discovered planet would be labeled HD 209458b. The letter B indicates it is the first planet found orbiting that star, while the letters continue alphabetically for subsequent discoveries like C or D. Once the scientific community has a consensus on classification, the IAU often invites the public to suggest or vote on names for these planets and their stars. This initiative engages astronomy enthusiasts and allows them to contribute to the astronomical lexicon. The chosen names can reflect mythology, literature, cultural significance, or relate to particular characteristics of the planet itself, adding an extra layer of story and connection to these distant worlds. As a result, the nomenclature and categorization of exoplanets not only serve scientific purposes, but also foster a connection between humanity and the universe. Each name holds the potential for wonder and discovery, sparking the imagination and deepening our understanding of the cosmic tapestry woven with countless planets, many of which may host their own unique stories yet to be uncovered. The naming of an exoplanet goes beyond mere identification. It often reflects cultural, mythological, or scientific significance, inviting a deeper connection between humanity and these distant worlds. Many exoplanets are named after mythological figures, highlighting the rich tapestry of human storytelling. For example, planets like Kepler 22b may possess cultural names that echo the traits and stories of gods and heroes from various cultures. This connection serves to spark our imagination, merging ancient histories with cutting-edge astronomical discoveries. Moreover, the features of these exoplanets sometimes inspire their names. Take the planet HD 209458b, known as Osiris. Named after the Egyptian god of the afterlife, this particular exoplanet features a striking atmosphere that scientists believe could support the study of atmospheric loss. The significance of this name relates not just to mythology, but also to what we can learn about planets with similar characteristics, and by extension, our own understanding of life and habitability beyond Earth. The naming process often involves international collaboration and public input, which can create a sense of global community surrounding these celestial discoveries. Different cultures contribute their own perspectives and interpretations, turning the naming of exoplanets into a celebration of our diverse understanding of the universe. This collective effort underscores our shared curiosity and desire to explore unknown realms, allowing a planet named after a cultural figure to be more than just a dot on a map. It becomes a representation of a collective human aspiration. The names of exoplanets are a bridge between the scientific and the cultural. They allow astronomers, storytellers, and ordinary people alike to engage with the cosmos in a more personal way. As we look to the stars and discover new worlds, the stories we weave through the names we give them enrich our understanding, reminding us of the intricate connection between science, culture, and the narratives that shape our quest for knowledge. The naming of exoplanets, those distant worlds orbiting stars outside our solar system, is increasingly becoming a collaborative effort that includes the public. Organizations like the International Astronomical Union have engaged enthusiasts and everyday people in the naming process, inviting them to submit and vote on names for these fascinating celestial bodies. This initiative does more than just make the names more relatable. It fosters a sense of ownership and excitement among the public regarding astronomical discoveries. When people participate in naming exoplanets, they become emotionally connected to these distant worlds. It transforms an abstract concept into something tangible and understandable. Think about it. Instead of merely reading about planet HD 209458b, which might sound like a complex code, citizens can help name it something meaningful, like nostalgia. Such connections can ignite curiosity about the universe and prompt further exploration into astronomy and science as a whole. Moreover, public involvement in naming exoplanets provides a unique platform for outreach. It encourages educational institutions, libraries, and community organizations to engage in discussions about space and science, sparking interest among young and old alike. When the public feels their choices matter, they are more likely to seek out additional information and share their newfound knowledge with others, creating a ripple effect that can enhance science literacy. Ultimately, by allowing the public to participate in naming exoplanets, we not only enhance engagement with scientific content, but also create a shared narrative about our place in the universe. This collaboration helps demystify science, bridging the gap between experts and enthusiasts, and fostering a more inclusive approach to understanding the cosmos. The names we give these worlds may reflect cultural diversity, history, and imagination, enriching the story of our universe and inviting everyone to join in the exploration. The life cycle of a star is a fascinating and crucial aspect when considering the habitability of its orbiting planets. Stars are born from massive clouds of gas and dust, and their evolution dictates not only their brightness and temperature, but also the environment around them. The life cycle is often divided into stages: the main sequence, red giant, and eventually the end stages like white dwarfs or supernovae. Each of these stages profoundly influences the potential for life on nearby planets. During the main sequence, a star shines steadily, providing a stable energy source. This is the most favorable period for habitability, especially if the planet resides in the star's habitable zone, where conditions allow for liquid water to exist. The duration of this phase can vary greatly. For smaller stars, like red dwarfs, it can last for billions of years, providing a long window for life to potentially develop. In contrast, massive stars burn bright but only for a few million years, an exceedingly short time frame for the emergence of life. As stars evolve into red giants, their outer layers expand and cool, profoundly altering the conditions on nearby planets. This change can lead to intense heating, stripping atmospheres, or rendering planets inhospitable. For instance, if Earth were to orbit the Sun during this phase, it would likely experience catastrophic changes that could make the planet uninhabitable. In the later stages, such as ending as a white dwarf, The diminishing energy output further reduces the chances for life nearby. The life cycle of a star shapes the environment for its planets, influencing the type of climate and potential for life. Understanding these stellar lifetimes and transformations allows astronomers to assess the habitability of exoplanets more accurately, illuminating countless possibilities in the quest for life beyond our own solar system. Each star's journey is unique, offering a varied landscape where life may or may not thrive. Studying dying stars offers us a remarkable window into the future of their exoplanets. When a star reaches the end of its life, it undergoes significant changes, such as expanding into a red giant, which dramatically alters the environment of any planets orbiting it. This transformation can lead to intense heat and radiation that may strip away atmospheres, boil away oceans, or even obliterate the planets altogether. For instance, when our own sun transitions into a red giant after several billion more years, it will expand beyond its current boundaries. The inner planets, including Earth, will face extreme conditions, potentially rendering them uninhabitable. By observing dying stars in various stages of their evolution, scientists can gather evidence about how different types of stars will evolve and how that will impact their planetary systems. Moreover, the study of dying stars also provides clues about chemical processes. As stars exhaust their nuclear fuel, they eject material into space, enriching the surrounding interstellar medium with heavier elements. These elements can eventually become part of new stars and planets, offering a glimpse into how the composition of exoplanets changes over time. Understanding these cycles gives us insight into the kinds of environments that might shape future worlds. Focusing on older stars allows astronomers to speculate on the fate of nearby exoplanets. By examining the changes happening in dying stars and their influence on surrounding planets, we can draw parallels to similar processes that might be happening in other systems. This rich tapestry of cosmic evolution helps us comprehend not just the life cycles of stars, but also the ultimate destiny of the worlds that dance around them. The lifespan of a star plays a crucial role in shaping the conditions on any orbiting planets, particularly regarding their atmospheres. A star's life cycle can span billions of years, but different types of stars have vastly different lifespans. For instance, a small star like a red dwarf can burn for tens of billions of years, while massive stars might only shine for a few million years before they explode as supernovae. This longevity affects how long a planet can maintain a stable atmosphere, which is essential for supporting life. During a star's main sequence phase, it provides a relatively stable input of energy. This consistency allows a planet's atmosphere to develop and evolve over time. If a planet orbits a star with a long lifespan, like a sun-like star, there's plenty of time for biochemical processes to unfold, potentially leading to the emergence of life. In contrast, planets orbiting shorter-lived stars might experience environments that change rapidly, hindering the development of complex atmospheres or life as we know it. When a star exhausts its nuclear fuel, it undergoes dramatic transformations that can drastically alter its output of energy. For instance, a star like our Sun will swell into a red giant before shedding its outer layers. Such changes can strip away a planet's atmosphere entirely or radically change its composition. If the atmosphere is lost, it can lead to surface conditions that are inhospitable to life, making the type of star and its lifespan pivotal in determining a planet's long-term habitability. Additionally, the stability of a star's energy output ensures that planets can reach a balance of heat and cold. This balance is essential for maintaining liquid water, a vital ingredient for life. Therefore, when considering the long-term viability of a planet's atmosphere, the lifespan of its parent star is not just an abstract detail. It holds profound implications for the planet's climate, the development of its atmosphere, and the potential for life to thrive. When we explore the vast cosmic ocean of exoplanets, we encounter two key concepts: habitability and the actual presence of life. Habitability refers to the conditions necessary for life to potentially develop, while the presence of life means that some form of living organism has successfully taken root. Understanding the difference between these concepts is essential for speculating about life beyond Earth. The first critical factor of differentiation is the availability of key resources. For a planet to be considered habitable, it typically needs a stable supply of water, a suitable atmosphere rich in essential gases, and the right temperature range that allows for the existence of liquid water. These conditions create a nurturing environment, yet just because a planet meets these criteria does not guarantee life. Life requires more than just resources. It involves complex biological processes that have evolved over time. Another important factor is the planet's geological and climatic stability. Planets that can maintain their environments over geological timescales are more likely to support life. This stability allows for chemical processes to occur, ultimately leading to the formation of life. However, even the most stable environments are not a guarantee that life will emerge. The emergence of life also depends on a multitude of evolutionary advantages and historical contingencies that we may not fully understand. Finally, the interplay between habitability and actual life is influenced by the chemical and physical dynamics at play. For instance, planets that possess the right ingredients may still miss essential catalysts for life to spark. On Earth, for instance, one small but significant factor, such as the presence of lightning or volcanic activity, can catalyze the formation of complex organic molecules. In the universe, the mystery of whether we are alone remains unsolved, as habitability is not just a checklist, it's a delicate dance of conditions that must align perfectly for life to flourish. To understand the potential habitability of exoplanets, scientists use sophisticated laboratory simulations that mimic the extreme conditions found in space. By recreating the atmosphere, pressure, temperature, and even chemical compositions of distant worlds, researchers can study how life, or at least the ingredients for life, might exist under those circumstances. This approach is essential because exoplanets are light years away, and direct observation is limited. In these labs, scientists utilize devices that can replicate the atmospheres of exoplanets by mixing gases under high pressure and varying temperatures. For instance, if an exoplanet has a thick atmosphere rich in carbon dioxide, researchers will create a similar environment, enabling them to investigate how organic molecules behave and whether they can form under those conditions. These experiments help determine the potential for complex chemistry, which is a crucial factor in assessing habitability. Simulations do not occur in isolation. They often involve collaboration across multiple disciplines, including astronomy, chemistry, and biology. As a part of these efforts, researchers study microbial life on Earth that thrives in extreme environments, like deep-sea vents or icy polar regions. Learning how these organisms adapt gives scientists clues about what forms of life could exist on other planets and informs their simulations. Ultimately, these lab simulations provide invaluable insights into the conditions that may foster life elsewhere in the universe. By understanding the limits of life on Earth, scientists can refine their search for habitable worlds, bringing us a step closer to answering the profound question of whether we are alone in the cosmos. The knowledge gained not only enhances our understanding of distant worlds, but also deepens our appreciation for the complexity of life as we know it. The potential discovery of intelligent extraterrestrial life presents humanity with profound ethical dilemmas that touch upon our values, responsibilities, and understanding of our place in the universe. First and foremost, there's the question of how we would interact with such beings. Would we treat them as equals, or would we impose our own views and behaviors upon them? This fundamental issue challenges our ideas about respect and coexistence, pushing us to consider the implications of imposing our beliefs and practices on societies that may be entirely different from our own. There are also concerns regarding communication. How would we convey our intentions to extraterrestrial beings? Would we run the risk of misunderstanding or misinterpretation, leading to conflict rather than collaboration? This dilemma emphasizes the importance of carefully considering our messages, avoiding the use of aggression or superiority. The ability to bridge the communication gap may be crucial in creating peaceful relationships based on mutual understanding and respect. Another significant ethical question involves the potential risks of contact. If we discover intelligent life, what responsibilities do we have to protect both our own planet and theirs? History has shown us that encounters between different cultures on Earth often lead to exploitation and harm. We must ponder whether humanity has the moral capacity to approach such a revelation with caution and responsibility. Every step taken in such an endeavor could have significant repercussions, not just for our species, but for any alien life forms we find. Lastly, we must reflect on how the discovery would impact our own self-identity and worldview. Meeting intelligent extraterrestrial life could challenge religious beliefs, philosophical perspectives, and even the very idea of humanity itself. These reflections compel us to examine our assumptions about life, intelligence, and what it means to be human, suggesting a transformative journey that could ultimately reshape our understanding of existence and our responsibilities within it. This dialogue about the ethical implications of extraterrestrial contact is not just a matter of speculation, but rather a profound inquiry into our character and moral compass as a species. Science fiction has played a pivotal role in shaping public perception and interest in the search for exoplanets. For decades, stories of distant worlds, alien civilizations, and interstellar travel have captured our imagination and prompted us to think beyond our own planet. Films, books, and television series have not only entertained, but have also educated audiences about the possibilities of life beyond Earth. Titles like Star Trek and The Martian have introduced complex ideas about space, planetary systems, and the conditions needed to support life in a way that is accessible and engaging. These narratives often explore themes of exploration and discovery, mirroring the very real scientific endeavors taking place today. As scientists began to discover and catalogue exoplanets, those planets orbiting stars outside our solar system, the public's interest surged. The excitement conveyed in science fiction made the concept of finding Earth-like planets not just a scientific possibility, but an exciting frontier for humanity. From the idea of a Goldilocks zone, where temperatures might be just right for life, to evocative worlds that might hold intelligent beings, these stories have turned abstract scientific concepts into relatable ideas. Moreover, science fiction has inspired actual scientific projects and missions. Books like Contact by Carl Sagan or films such as Interstellar have sparked imaginations and encouraged young minds to pursue careers in astronomy and astrophysics. The wildly popular series The Expanse also delves into the nuances of space travel and the realities of living on other planets, leading to discussions in households worldwide about what exoplanets might be like. Each new discovery in astrophysics tends to evoke a wave of creative storytelling, feeding back into the public's curiosity. As we stand on the cusp of potentially discovering habitable worlds and perhaps even signals from intelligent life, the relationship between science fiction and science, especially concerning exoplanets, becomes even more fascinating. In a sense, these narratives not only reflect our aspirations, but also help steer the conversation towards understanding our place in the cosmos. The shared wonder of these distant worlds, shaped by science fiction, ultimately nourishes both our imaginations and our scientific endeavors. Science fiction has long captured the imagination regarding exoplanets, planets that lie beyond our solar system. One of the most popular scenarios involves humanity establishing colonies on distant worlds. This concept often portrays humans escaping an Earth ravaged by environmental disasters, wars, or overpopulation. In these tales, shining cities arise on planets that mimic Earth's conditions, inviting exploration and settlement where the possibilities seem limitless. Another captivating scenario features intelligent extraterrestrial life. Many stories revolve around the first contact with alien civilizations residing on exoplanets, challenging our understanding of life itself. These narratives often delve into the complexities of communication and cooperation as humanity grapples with the ethical implications of interacting with beings from another world. The rich diversity of imagined alien cultures invites listeners to ponder what life may truly be like, sparking both excitement and trepidation about our place in the cosmos. In addition to colonization and alien contact, stories frequently explore the harsh realities of life on exoplanets. Writers envision worlds with extreme climates and bizarre ecosystems where survival becomes a significant challenge for settlers. These scenarios often serve to highlight humanity's resilience and adaptability, whether depicting thick jungles on gas giants or frozen tundras of icy worlds. Such extreme environments invite reflection on the limits of human ingenuity against the backdrop of breathtaking alien landscapes. Lastly, time travel and alternate realities are common themes involving exoplanets. Some narratives propose exoplanets as gateways to different times or dimensions, leading to thrilling adventures that defy the boundaries of traditional storytelling. In these plots, characters navigate not just the vastness of space, but the very fabric of time and reality itself, allowing for exciting explorations of fate, choice, and consequence. The allure of uncharted worlds and the mysteries they hold continually fuels our fascination with the unknown, encouraging us to dream about what lies beyond the stars. Artistic interpretations of exoplanets often serve as a reflecting pool for our collective hopes and fears as a society. When scientists discover planets beyond our solar system, the artistic community eagerly imagines what those distant worlds might look like. These creative visions are not just whimsical illustrations, they embody our aspirations for the universe, igniting dreams of exploration and the possibility of finding life beyond Earth. For many, these artworks symbolize hope, suggesting that we might one day connect with other intelligent beings or discover new forms of life that could inspire cooperation and understanding. Conversely, the interpretation of exoplanets can also reveal our anxieties about the future. Some artistic representations highlight hostile environments, portraying barren landscapes or climates capable of supporting life but rife with dangers. These visions can reflect societal fears about our own planet's changes due to climate change, resource depletion, or technological advancements. The images remind us of the fragility of life and the potential consequences of our choices, thereby inviting deeper considerations about how we treat our own world. Moreover, these artistic interpretations often delve into the philosophical implications of discovering exoplanets. They ask profound questions about humanity's place in the cosmos. Are we alone in the universe? What would contact with extraterrestrial civilizations mean for our identity and values? Such art can provoke discussions that extend beyond astronomy and delve into ethics, existentialism, and our understanding of consciousness itself. In this way, the art surrounding exoplanets becomes a conduit for exploring what it means to be human. Overall, the artistic exploration of exoplanets serves as a bridge between science and society, linking our empirical understanding of the universe with the complex emotional and philosophical framework within which we navigate life. These creative expressions encourage us to dream while also staying grounded in the realities of our existence, making them a crucial element in the ongoing dialogue about our future among the stars. Kepler 186f stands out in the ever-expanding universe of exoplanets for several compelling reasons. Discovered by NASA's Kepler Space Telescope in 2014, it is notable for its remarkable similarity to Earth, earning it the title of the most Earth-like planet discovered to that date. One of its most striking features is its location within the habitable zone of its star, a region where conditions are just right for liquid water to exist, a crucial ingredient for life as we know it. This exoplanet orbits a star that is a cooler and smaller type, known as a red dwarf. Red dwarfs are abundant in our galaxy, but their faintness means the planets around them experience different conditions compared to those orbiting larger stars like our Sun. Because Kepler 186f receives about 1/3 of the energy that Earth receives from the Sun, its temperatures could permit the presence of liquid water if the planet has a suitable atmosphere. This puts it on the shortlist for potentially harboring life. Furthermore, Kepler 186f is approximately 1.1 times the size of Earth, which places it firmly in the category of a super-Earth. Its slightly larger size suggests it could have a rocky surface. Scientists believe such characteristics make it capable of supporting a climate that could be similar to ours, especially if it has a stable atmosphere. This possibility ignites our imagination about what types of life forms might exist there. The discovery of Kepler 186f opens the door to profound questions about our place in the universe. As we explore these distant worlds, we gain insights into the diversity of planetary systems and the potential for life beyond our own. Each new finding leads us to wonder, just how unique is our Earth in the vast cosmos, and could there be distant cousins of our own planet waiting to be discovered? WASP 121b is a fascinating exoplanet that lies about 800 light-years away from Earth, and it has garnered attention due to its extreme environmental conditions. This particular planet is classified as a hot Jupiter, which means it is a gas giant similar in size to Jupiter, but orbits its star at a blistering close distance. As a result, WASP-121b experiences unimaginably high temperatures, with daytime temperatures soaring above 2,500 degrees Celsius. This is hot enough to vaporize metals, creating a unique and extreme atmosphere. One of the most intriguing aspects of WASP-121b is its distinct weather systems. Unlike Earth, where we think of weather in terms of rain and snow, WASP-121b experiences rain made of molten metals, such as iron and magnesium, due to those extreme temperatures. This scorching weather is driven by the extreme pressure of its atmosphere, which, like a pressure cooker, contributes to the intense climatic conditions. Strong winds sweep across the planet at incredible speeds, leading to highly dynamic and turbulent weather patterns that scientists are excited to study. Additionally, WASP-121b exhibits an unusual day-night temperature contrast. One side, perpetually facing its star, is scorched under relentless sunlight, while the opposite side lies in eternal darkness. This stark division leads to dramatic atmospheric conditions. Scientists suspect that the heat from the daytime side is transferred to the night side, creating some of the fastest winds observed in planetary atmospheres, reaching velocities of up to 2,500 kilometers an hour. Researchers are particularly intrigued by the chemical composition of WASP-121b's atmosphere.